Okay, it's full one, so let's get started. Okay, hello everyone, welcome back to KAIST SoC Colloquium. This is our third time in this fall. I'm Min Hyuk-sung in KAIST SoC, and today we also have a very special guest, Andreas Geiger here. And Andreas Geiger is a full professor at the University of the Tübingen in Germany. And before that, he was also a visiting professor at ETH3 and also a group leader at the Max Planck Institute for the Intelligent Systems. And he leads his PhD from the Karlsruhe Institute of Technology, KIT, and also he studied at EPFL and MIT. And Andreas is also famous for the KT data set that most of you would know if you are working on the computer vision area. And KT is one of the most famous benchmarks for many vision tasks, especially related to the autonomous driving, such as the optical flow, the scene flow, and the object detection, segmentation, and the tracking, and also motion estimation. And his work also has been recognized with several prizes, including the IEEE, the Penny, the Young Investigator Award, and also the Heinz Mayer the Leibniz Prize of the German Science Foundation, and also the German Pattern Recognition Award. And he also received the CVPR Best Paper and also the Best Paper, the runner-up, the awards in 2013 and also in this year, in 2021. And everyone also know that the CVPR is basically the top tier conference in the computer vision. And he also received the Best Paper Award at the GCPR 2015 and also 3DB in 2015, as well as the Best Student Paper Award at the 3DB 2017. And in the 2019, he was also awarded the starting grant by the European Research Council. And he's also the board member of the ALICE initiative and also the associated faculty of the International Max Planck Research School for the Intelligent System. And he also coordinates the ALICE PhD and the postdoc programs. And also he regularly serves as the area chair and also the associate editor for the several computer vision conferences and journals, including the CVPR, ICCB, ECCB, PEMI, and also IJCB. So I'm very to welcome Andreas Geiger today, and thank you for Andreas for the joining. Let's give a warm welcome to him. And today, Andreas will talk about the neural implicit representation for the 3D vision. And also for the audience, if you have any questions, please leave the questions in the Zoom chat. And also we are streaming this talk, but the chat in the YouTube streaming is disabled for now. So if you leave the questions in the Zoom chat, then I will go through them after the talk. Okay. So let me switch the sharing.
Thank you very much for this nice introduction, and it's a great pleasure to be here today. Let me share. Okay, is it visible?
Yes.
Great, okay. Super. Yes, as already mentioned, I'm going to talk about neural implicit representations for 3D vision. Some of you might already be a bit familiar with this. This is a research area that my group has been exploring over the last 2 years or so and has really grown tremendously and has an impact in different areas. But before we go there, I want to give you a brief high-level overview of what we are doing in our research group. Our research group is called Autonomous Vision Group, AVG, because we are interested in both fundamental advances in computer vision, but also in combining this with action in building intelligent systems that can go around in the world and act and interact with the real world. In particular, we're interested in self-driving cars. That's a problem that's dear to my heart already since 10 years or so. The Kitty dataset has already been mentioned. This year, we have just released the Kitty 360 dataset. An archive paper is coming out this week, probably. And so we are also trying to make progress on the benchmarking and dataset side. But also we are focusing on the sensory motor control problem itself. I want to show you a little video here. And for this, we're typically learning and evaluating in simulation. So we're using the Kala simulator, as you can see here. And this is one of our latest models that appears in 2 weeks at ICCB. It's called NEAT, Neural Attention Fields, and it allows the car to be trained end-to-end just based on the images and the true or the expert vehicle decisions, as well as semantic segmentation, and then can drive autonomously in this Scala city with all kinds of complexities, as you can see here. We are also interested in getting a good understanding in terms of geometry and materials and lighting of the world. So this is an example of a project that we have been carrying out recently of estimating geometry and materials of real-world objects. And we are currently in the process of extending this towards full scenes so that we can generate photorealistic data sets, if you will, in this case of indoor scenes, similar to for example, the ScanNet dataset or the Matterport dataset, but including materials. We are also interested in probabilistic generative models. We are making, we're working towards a theoretical understanding of probabilistic generative models, but also certain applications. And one application you will see later in this talk, which is this CVPR 21 paper that has received the Best Paper Award at CVPR this year. And then the main topic of this presentation will be 3D representations in general, which we care a lot about because it's not so clear how the world should be actually represented and what's a good representation that works well with the recent advances in representation learning. The talk is structured into 4 parts. In the first part, I'm gonna give an overview over implicit neural representations and introduce them and show you some applications. In the second part, I'm going to talk about how these representations can be trained from image information alone with 2D supervision, not assuming 3D supervision. In the third part of the talk, I'm gonna review neural radiance fields, which is also a work that follows up on this idea of implicit representations. And then in the fourth part, I will talk about generative models that allow us to synthesize novel environments based on this radiance field idea. Okay, so let's start with implicit neural representations. How can we reconstruct the 3D world? Well, let's first have a look at a traditional 3D reconstruction pipeline, which typically works something like this. You're given a set of input images, then you construct estimate the camera poses, for example, using bundle adjustment. And then once you have the camera poses, you can rectify the images and find dense correspondences. So you can do stereo or multi-view reconstruction to give you partial 3D reconstructions of the environment. And then you can fuse these into a more complete 3D reconstruction, which you can then continue optimizing, for example, right? This is a very data-driven approach. However, in the last 10 years or so, there has been a surge in 3D data becoming available on the web, for example, scanned data or CAD repositories, as shown here at the bottom left, as well as larger scans of entire indoor buildings, indoor environments like buildings here in the case of the Matterport 3D dataset. And so it's natural to ask, well, can we actually reconstruct, can we use this information to reconstruct with less input information? Can we learn 3D reconstruction from data, right? If humans look at a scene, they can also reconstruct pretty well in their head what the scene looks like just by looking at a single image even. So here's one of the simplest formulations you can think of. Given a single 2D image, just a pixel matrix, we have a neural network that tries to produce a 3D reconstruction of that object that's visible on that 2D image. Okay. And it has to reason not only about the visible parts of the object, but also about the invisible part of the object. So it needs to be trained on a big data set in order to reason correctly also about what's hidden. Now, what's relatively clear to us is how we can take this image and compress that into a compact representation. We can just use standard 2D convolutional neural networks to get a compact representation out of that image. But what's less clear is what should the output representation look like? right? So how should we actually represent the output such that it's easy for a neural network to predict that output representation? In other words, what is a good output representation? In the context of deep learning, a variety of representations have been investigated, starting from the very classical one, the standard voxelization, just an equidistant discretization of 3D space into voxels. Here on the top, you can see, just for simplicity, a 2D visualization. At the bottom, you can see the corresponding 3D visualization. And you can see how such a voxel-based representation looks like. And it's, of course, easy to predict because you just need a 3D deconvolutional network to predict each of these voxels being empty or occupied, right? The second one is that people have looked at from 2017 on with this first seminal work on point set generation networks is point sets. Point sets represent the shape just as a collection of points, but of course they don't capture any topology. So there's no watertight surface, if you will. And also these approaches are quite limited in the number of points that they can predict typically. And then finally, which is maybe the most common representation in computer graphics, people have also tried to predict meshes, like in this case AtlasNet. But meshes are really a hard to predict output representation for neural networks because it's very easy to create self-intersections, right? You need to predict something, you need to predict the vertices and the faces such that all the faces are roughly the same size and that none of them self-intersect. And that's really hard. So in the case of AtlasNet, that has been done using a collection of patches, but the result is not watertight. There's an alternative to this. If you know already the object shape, for example, if you, for example, want to reconstruct the human face or the human body, then you can also take a template and just deform the template. But then you have to know roughly what is the shape that you want to predict. So this is also not an easy to predict output representation for neural networks. And all of these representations suffer from the fact that they are discretizing space in one way or the other, because they are explicit representations. So what we then proposed or thought about in 2018, 2019 is, well, do we actually need to represent the 3D shape explicitly? Can't we just represent it implicitly? In this case here as the decision boundary of a classifier, right? All the previous representations that I've shown are explicit representations, but can we also just use an implicit model? And as an implicit model, we just use a neural network itself. So we use a neural network as the representation itself. So here on the right, you can see an example. Here's some red points and some blue points, and there's a very simple linear decision boundary that corresponds to the surface. And at the bottom, you can see the equivalent in 3D space, where also the red points, which are inside the object, must be separated from the blue points, which are outside the object. And they are separated from them through the decision boundary, which in this case has the form of a bench. Right? So the bench is the shape that we're interested in. And mathematically, this is very simple to describe. We have a function, a neural network with parameters theta that maps a 3D location, one of these points, and a condition that is maybe a 128-dimensional vector that comes from a 2D convolutional network that encodes a 2D image. So we take that vector here, and for that image and for that 3D location, we want to predict the occupancy probability. Right? We want to predict if that point is outside or if that's inside. So that's a very simple way of formulating shape prediction as a classification problem. Now, in this case, the function f models a so-called occupancy field because we are predicting occupancy probabilities. But it's also possible, of course, to predict other quantities, for example, sign distance values, as done in Park et al., which was also a paper from 2019, or densities, as we'll see later in the case of radiance fields. So there's all kinds of output attributes that you could predict with such an implicit representation. Yeah. Maybe one comment I have here is that if we talk about implicit representation, what we mean here really is a neural implicit representation, where the function itself is represented by a neural network. In the past, people have also looked at implicit representations, but still discretized 3D space. For example, in volumetric fusion, you're using an implicit representation where at discrete locations in a voxel grid, you're representing for each of these voxels, you're representing these voxels with a sign distance value. But here, there's no such discretization. There's just a function that can be arbitrarily complex or arbitrarily smooth, which continuously represents this occupancy field. Okay, so how would a architecture that achieves this look like? Well, this is the first architecture that we have used in our 2019 paper. On the top here, you can see an encoder, which is just a general depiction of any possible encoder of any quantity that we want to encode. For example, in the case of a 2D image here at the bottom, this is just a 2D convnet. In the case of a point cloud, this is a point net, for example. Or in the case of a coarse 3D shape that's voxelized, this could be a 3D convolutional network. So it doesn't matter how you encode the input, it depends on your input. But all of these result in a global latent code. Let's say this is a 128-dimensional vector C that we want to condition our network on. And our network itself takes this code, and it also takes 3D point locations. So here we have the number 3 because we have X, Y, and Z. And we're not only inputting a single point, but we're inputting T points in the order of a few thousand, because it would be inefficient to query this network individually for single points. And it's possible, memory-wise, to pass multiple of these points in parallel through this network. So we're using a few thousand points here that we query in parallel. So we're taking these T points, these T 3D points, and the global representation of the conditioning, the input, and we're passing this into 5 ResNet blocks, 5 blocks of a residual network here, fully connected residual network, where the points are directly input, and this condition is input, in this case, using conditional batch normalization. But in later work, we have also found that simpler conditioning schemes also work, like just adding this information or concatenating this information. Here you can see this residual connection, and this is a block here that repeats for 5 times. So we have 5 these blocks in our network, and the output then is for each of these T points, one value, and that value is the probability of occupancy for that point. Okay, so very simple architecture. How can we train this model? Well, it's a very simple classification task, so we can just use the standard binary cross entropy loss, and that's what we do. So here's the sum for all these k points that we input. This is the mini batch. We compare using the binary cross entropy loss the prediction of the model here on the left for a particular 3D point and a particular input condition C. This is the image encoding, to the ground truth occupancy of that point, which is assumed to be given. This is fully supervised in this case. So we assume that we have the ground truth shape, and it's watertight, so we can evaluate if a 3D point is inside or outside. And then we can just sample random points in 3D space, evaluate if these points are inside and outside, inside or outside, and based on this, build up our training set, and then minimize this binary cross entropy loss. We can also extend this objective to a probabilistic generative model, in this case a variational autoencoder, which we call here a variational occupancy encoder, where, if you're familiar with VAEs, we have now this VCE term here as the reconstruction error, and an additional term here on the right that measures the divergence between a Gaussian distribution in latent space and what is predicted by an encoder here in green. So we have another neural network now with parameters psi that takes a 3D point set and tries to predict the latent code. And so it's just mapping the formulation of a VAE to this problem here. And then we can train this model in an unsupervised fashion on a collection of 3D shapes. And we'll see that in a second. Now, one thing with these implicit models is that, of course, because they are implicit, the shape is not directly given as an output of these models, right? And so we have to extract the shape. And if we would just query very densely all the points in 3D space, that would be very inefficient. So what we do instead is we use a multi-resolution technique that incrementally builds up an octree by querying the occupancy network. So let's assume this gray curve here is the shape. Again, it's just a 2D visualization here, but of course everything is in 3D. So we start with a regular grid that's not too coarse, not too fine, and query each point on this grid. So for each point on this grid, we query the occupancy network. And if a point is inside the shape, hopefully the occupancy network will tell us, well, this is inside, and if it's outside the shape, it's outside. So inside is red here, and outside is cyan. So we do this for all the points. And what we then do, or what we then know, is that, well, if there is a transition from an inside point to an outside point, that is this is a location where the surface must actually pass through, right? So we are marking all the voxels that are at transitions in red. So for example, this one here, because it transitions from red to cyan. And then we can subdivide this further, of course, just the ones that are red here. And this is why we don't have to query the space densely, because a lot of the space is actually free space. So we just query what is actually needed. And then for these new query points, we get again the inside-outside result from the occupancy network. And we can do this n times until we arrive at the desired resolution. And we can even refine the surface here using double backpropagation by optimizing along the normals. But in fact, what we found is that if we just do one or two more steps here of refinement, we can get to a resolution that's hard to improve. So we just keep on doing this until we reach the target resolution that we want. And then from this, we can simply extract the triangular mesh using the marching cubes algorithm. And this takes, depending on the size of the scene and of the object, takes about 1 to 3 seconds in total. Okay, so we've seen how we can learn these models, and we learn them on, in this case, on large collections of data where we have multiple categories, in this case of ShapeNet, and all of the input images for each of these 3D object, we generate an input image by rendering it, and then we encode that input image, and we give this as the condition to the network, and then these randomly sampled 3D points for training the model, and then at test time we give the model a new image, a 2D image as input, and ask the model what is the 3D shape for that, right? So I want to show you some results here. Hope you can see that. We have on the left here the 2D input image, and on the right the reconstruction that's produced by the respective method. This is a voxel-based approach, a point-based approach, a mesh-based approach, and the implicit model. And what you can see is that because it's an implicit model, it doesn't have any difficulty in inferring complicated topologies with holes, as you can see here, right? It's not, it's hard for a mesh to do that, for a mesh-based approach to do that, but for an implicit model, it's easy because topologies are intrinsic to that representation. Topology changes are intrinsic to that representation. So here's a comparison to the ground truth. Here are some results for point cloud completion. So in this case, the input is not a 2D image, but it's a sparse and noisy point cloud. and we ask the models to predict the 3D shape from this input. And now we're using a point net to encode it. Here's the result for a point baseline. And this is the result for the implicit representation. And here's the ground truth again. And we can also do voxel super resolution. Now we have as input a coarse voxelized shape that we encode using a 3D encoder. And on the right, you can see the details that our model is able to predict. Again, these are, of course, novel shapes that haven't been seen during training. What you can see now are latent space interpolations. So this is the generative model version of this model, where we train that model, this VAE, on a large collection of 3D shapes. Now there is no conditioning in this case, and you can see that we can then interpolate between latent codes and generate novel shapes that are not part of the training set. So I can see there's some issues with that sometimes, but in general, it produces plausible shapes. Great. Okay. So the next thing that we wonder is, well, can we use these models also to represent appearance? And in this case, what we did is, it's a model called Implicit Surface Light Fields. Given not only the 3D location, but also the light direction and the view direction, assuming a point light source, but we can of course generalize this to entire environment maps. So given these three things here now, 3D point location, the view direction, and the light setting as an input to a neural network, we are predicting the color value, right? And we can combine this also with the occupancy network to predict both the geometry and the view dependent appearance. And how does this look like? This is an example of ground truth geometry. On the left, you can see the input image. That's again the condition to what we want to infer. And on the right, you can see the result of a simple 2D image-to-image translation baseline, which doesn't look great because it's a very hard problem, of course, to do this entirely in 2D space. But when we move to 3D space, so this is now changing the light location, you can see that shadows moving a little bit, but it's very blurry. But if you move to 3D space, it's automatically consistent, and you can see how much more detail you get. You can see that depending on the viewpoint that we choose and the light location that we choose, we can see specularities and shadows moving and so on. This is all, again, inference results for a single 2D image as input. The next thing that we're wondering was, well, can we also use this to represent motion? And we found that extending the idea of occupancy networks to predict in 4D space is actually quite hard. And the problem for this is the curse of dimensionality, and also the limited availability of datasets for motion, for objects in motion, for 3D objects in motion. So what we do instead is that we represent the shape only at a particular time instance using a 3D occupancy network, as we've just seen, and then represent the motion by a temporally and spatially continuous vector field. Now, this is a 4D quantity that we have to predict still, but the advantage of this vector field is that it is smooth everywhere, as you can see here in this illustration on the top. In contrary to predicting directly the 4D shape over time, which has a lot of discontinuities, in particular where the human body ends at the surface of the human body, which is hard to represent, representing the vector field is easier because it's smooth. And we can relate the 3D location and the velocity, of course, through a very simple ordinary differential equation, as the gradient of the location is simply the velocity. And because we know how to backpropagate gradients through an ordinary differential equation, we can make this part of our model and backpropagate from the target, or from the time where we supervise back to the time 0 where the shape is represented. And the nice thing about this is that this automatically establishes correspondences despite that we don't input correspondences. So here's an example. Here we have the naive, well, this is the input, is a very noisy point cloud. And here we have the naive result of a 4D occupancy network where you can see it's quite impoverished. This is a point-based method, and here you can see the result of this occupancy flow approach. And you can see that it is much more detailed. Of course, it's far from perfect, but also the input is very noisy. But it's much more detailed, and also it automatically, despite only being supervised with a reconstruction loss, it establishes correspondences which you can see by the colors not changing over time. So individual object parts are labeled with the same color, as you can see here. And this is not something that we input to the model or trained with, but it's something that emerged automatically. So this was our approach to make these models work on smaller data sets that capture both space and time. Okay. One of the limitations of these implicit representations that we found is that because of their structure, the shapes that we infer are typically overly smooth. And this is particularly bad if we go to scenes. And there's two problems with this, or two reasons for this. So here we can see an illustration of the standard occupancy network where we have an input, let's say an image that's encoded into a global feature vector. And then we have this multi-layer perceptron, this ResNet that takes a 3D location and these features and produces the occupancy probability. The first problem is that we have a global latent code that doesn't capture any local information. And therefore, it's very hard to represent the exponential complexity of all constellations of 3D objects in a room, for example. And also, it is a very naive, fully connected architecture that doesn't capture relevant aspects such as, let's say, translation equivariance, as we are very familiar with in convolutional networks. So we can't easily exploit this here. And this leads to results like these. So here we trained on a collection of synthetic objects that have been placed like in an artificial scene onto the ground floor. And here on the left, you can see the inference result of an occupancy network. And of course, except for the ground floor that has been reconstructed well, none of the objects is recognizable. What we proposed here in this EasyCV work is therefore to combine the idea of implicit representations with the idea of convolutional neural networks. And we call this convolutional occupancy networks. And so the idea here is to take the input and not encode it into a global feature vector, but to encode it into a 3D volume. Now this volume is relatively coarse, maybe 64 by 64 by 64, but we can apply this idea in a sliding window fashion to reconstruct much larger scenes. And also, what we do here is, if we query a feature from this volume, we query it using trilinear interpolation, so that we can query from any continuous location, we can query this volume. So we query using trilinear interpolation from the neighboring voxels for which we have predicted information using this 3D encoder. And then, of course, this allows us to utilize 3D convolutions and the properties of these 3D convolutions, the equivariance properties. So we take these features, we query these features using interpolation, and then we use the 3D location, and then with a more shallow network, we predict the occupancy probability. And this allows us to do two things. First of all, for single objects, which is not shown here, for single objects, it allows us to converge much faster than the original occupancy network. But then also it allows us to reconstruct entire scenes. This is scene level reconstruction, where we trained on synthetic scenes even, and then applied these models to real world scans. So there's even a domain gap here, but still we get some relatively decent reconstructions, and we can scale this up to reconstructing entire buildings, like in this case here on the Metaport 3D dataset. So this allows us to lift these implicit models to reconstruct larger scenes as was previously possible. Great. So this was a short intro to implicit representations and applications. In the second part, I want to talk about differentiable volumetric rendering, which is a way of supervising these models using 2D supervision. All the approaches that I've showed you so far have required knowledge about, well, have required 3D supervision. For all of these models, we had to have a watertight 3D model available, and we had to know for each point that we train with if it's occupied or not. But in reality, that's often not the case. Often we don't have this information. And so the question is, well, can we train these models now also with 2D supervision, just with images, as has recently been shown for mesh-based representations or voxel-based representations? The architecture that we're using here is very similar to the one that you've seen previously. So again, we have an image that's encoded into a latent code, and then we have a set of points that are input to such a residual network. But in this case, because we want to learn only based on images, we have one model now that predicts both the occupancy and the color information using two shallow heads that are attached onto this residual network. And for each of these 3D points, we predict an occupancy and a color value. Now the question is, if we want to train this model using 2D images, what do we need? Well, clearly we need to be able to render the images in the first place, and that's the forward pass of the neural network. And then if we want to train that neural network, we also need to backpropagate gradients. That's the backward pass. So we'll talk about both these forward and backward pass now. The forward pass is simple. So here's an illustration on the right where you see the shape represented in gray, where the thick gray line here is the 0 level set, or the level set that we're interested in, the threshold tau here, let's say 0.5 level set. Exactly in between 0 and 1, this is where the surface is supposed to be. And then we have, of course, we have in front of the surface, we have smaller values, and behind the surface, we have larger values. Just to illustrate what the shape looks like in bird's eye view perspective. And then here we have the image plane and the camera center, and we have a pixel U, and the camera center and the pixel U together define a ray through 3D space. Right? So what we do now for rendering an image is that for all the pixels U, we find the surface point P hat along that ray W, and we can do this by ray marching. So we query the occupancy network at equidistant, or the occupancy head at equidistant locations along the ray, and then we can do a route finding in logarithmic time using the second method here in order to get the surface point location P hat. And then we evaluate the texture field T, or the texture head at the location, which gives us the color, and we insert that color at pixel U into the image that we render. And if we do this for all the pixels in the image, we have rendered the entire image. So that's easy, but how can we actually now implement the backward pass? How can we compute the gradients that are required to update the parameters of the neural network based on image information? In order to understand this, let's first step back a little bit and understand how implicit functions, what implicit functions are, and how implicit differentiation works, because we need it. An implicit equation is a relation like this, where y of x is defined only implicitly. We don't have a direct explicit definition of y of x, but only implicitly through such an equation. Implicit differentiation then computes the total derivative of both sides, the left-hand side and the right-hand side, with respect to the quantity that we are interested in this case x, and then solves for the partial derivative of y with respect to x. So in this example here, we have f with respect to x and x with respect to x, which of course is 1. And here we have f with respect to y times y with respect to x. And on the right-hand side, we have a constant, which is of course 0 with respect to x. So I've just used the total derivative here and the chain rule on the left-hand side. Let's make it a little bit more concrete. Let's assume we have the equation for a circle here, which is an implicit equation. And now we can, through implicit differentiation, find the gradients of this expression here. So on the left-hand side, we differentiate with respect to x. So we get 2x, and then we get 2y times y with respect to x. And on the right-hand side, it's a constant, so we get 0. And then we can rearrange this expression here for y with respect to x. And then this results in minus x over y. So what you can note here is that y itself is present in this term, which would of course not be the case if this would be an explicit equation. But this allows us to define the gradient everywhere on this circle. And you can also see that the circle is not a function, it's actually a curve, right? So it's not something that we could express explicitly, but we can still compute the gradient everywhere on this circle. Okay. So how can we use this now to define the backward pass in these implicit models? Well, what do we need to do? What do we want to do? We have a prediction now. This is the predicted image, and we have an observation. The prediction we call I hat and the observation I. And of course, what we want to do is we want to minimize the loss between these two. We want to make them become similar. We want to change the parameters of the model such that the prediction becomes similar to the observation. For example, we can go over all the pixels U and compute the L1 or L2 per pixel difference between these two images. Now, in order to update the parameters of the neural network, what we need to find is, of course, the gradients of this loss function with respect to the parameters of the neural network. So we can use the chain rule to compute the derivative of the loss function with respect to the parameters, which is the sum of all the pixels times the loss with respect to I hat and I hat with respect to theta. And here, so the left term is of course simple. The question is now how to compute the right-hand term. The right-hand term is equal to this expression because again we need to use the rule of the total derivative because both t, the texture network, depends directly on the parameters theta, but also of course p hat depends on theta because if I change the parameters of the network, the geometry changes, so also the intersection point changes, right? So both t and p hat depend on theta, despite we don't explicitly mark this dependence on theta. But that's the reason why we need to use the total derivative here. So we get this expression, and well, this one and this one are easy to compute. This is just standard backprop in a neural network. We can backprop with respect to any of the variables, we get the gradients. But how can we compute this red expression here? The derivative of the surface intersection with respect to the parameters of the network. And for this, we use exactly the rule that I've introduced on the previous slide of implicit differentiation. We take the level set constraint here and implicitly differentiate it. And this leads to an analytic solution for this gradient here. And then once we have this analytic solution, and I will come back to this in the next slide, we can of course update the parameters of the neural network. Here you see an illustration where both the geometry and the texture are updated based on this observation to make the prediction come closer to the observation. So we have an analytic solution, and there's no need for storing intermediate results as, for example, when you do differentiable rendering in voxel-based representations. Now, very briefly, how did we arrive at this expression here? Well, if you look at this representation again here that we've seen before, and we consider this ray that goes through the camera center and the intersection and the pixel U and intersects the surface here, we can write this ray as the camera center R0 plus dW, which is the direction of the ray. And then we can, as already mentioned, implicitly differentiate this level set constraint here, where we have to use the total derivative on the left side and the right is a constant, so it's 0. So the derivative of this expression with respect to theta is just W times d hat with respect to theta, because only d hat, the depth, depends on the parameters theta. And now we can solve for this expression here. And if we rearrange the terms, we arrive exactly at this expression that I've shown you on the previous slide. So it's a simple application of the rule of implicit differentiation. Okay, so let's look at some results. What we can do with this model now is we can use 2D supervision to train conditional models, as we've done before, where at inference time the input is just a 2D image and we want to infer 3D shape. But now during training time we don't have we don't assume that we have 3D supervision available, but just the images. So here's a mesh-based baseline. Here's a mesh-based baseline that uses 3D supervision. And this is the result of this approach. You can see also there's some errors here, which is due to the fact that this is actually very hard here. It's a very textureless object, and so it's hard to predict. Here's another example. This is a car as an input conditioning. This is what the mesh-based approaches predict after training, and this is what we predict with our model that's trained only with 2D supervision. And of course, we can use this model also to supply 2.5D supervision. For example, if you have a Kinect camera, we can also use this information for training these models. Yeah, this is on ShapeNet, but we've also demonstrated that we can use these models to like basically overfit a single model, an unconditional model, on a particular scene, in this case on a DTU dataset, and use this for plain naive 3D reconstruction. And this also works with real data, as you can see here. But on the DTU dataset, of course, we can't deploy a conditional model just because the dataset is too small for training a conditional model. Good. Okay. So the last two parts are relatively short. So I'm coming close to the end of this presentation. One work that also uses this idea of implicit representations that has made a big splash is called neural radiance fields by Mildenhall et al. At ECCV 2020. The idea of neural radiance fields is very similar to occupancy networks, except that the input and the output are slightly different. So here the input is the 3D location and also the viewing direction, because we want to model view-dependent appearance. So this is similar to the surface light field model that I've shown you. But the output is now the RGB color and a density value. It's not the occupancy anymore, it's a density value. And the task that has been considered here is also slightly different. It's not 3D reconstruction, but it's rendering a scene from a novel viewpoint as photorealistic as possible. But otherwise, it's very similar. It's using a ReLU MLP that maps this input to this output here. And conditioning on the view direction allows for modeling these view-dependent effects. One thing that differs from occupancy networks or DVR is how the images are rendered. In this case, volume rendering is used, not surface rendering. And volume rendering works very similar to traditional ray tracing. You shoot a ray through the 3D scene, and then you don't have a surface definition. You don't have a surface defined. You just have occupancy values. So what you do is you sample this ray at certain locations, and then you do alpha composition of the colors depending on the occupancies that you have observed. Now, the disadvantage of this is that this is a little bit slower because you have to sample more points on the ray for this rendering to be precise. But the advantage is that you can now apply this to more general scenes. In the case of DVR before, what I didn't tell you is that DVR required masks as supervision. Here you can train on arbitrary scenes without input masks, which makes this model really nice. And probably you've seen the results of this model, which look really photorealistic. So you can render these scenes that have been captured from novel viewpoints in a very realistic manner. Now, one difficulty with this, one problem with this model is that, as mentioned, it's quite slow to render. It's even slower to render than the DVR model that I've shown previously. So, for example, for rendering a 800 by 800 pixel image, this model takes about 56 seconds. And we were interested in, well, can't we render faster? And what we did is, here in this work, KiloNeRF, that will also appear at ICCV soon, that we've demonstrated that actually you can get the same fidelity as NeRF, or even a little bit better fidelity, by instead of representing the entire scene using one big and heavy neural network, to represent the entire scene with thousands of very small and tiny neural networks. And combining this with techniques from the computer graphics community, such as early ray termination and empty space skipping. And so you get a rendering improvement of 3 orders of magnitude, as you can see here. Just to illustrate what dramatic difference this makes, here on the left you can see the NeRF rendered in real time, which leads to a 19 by 19 pixel image. While on the right-hand side, you can see the rendering of KiloNeRF at real time, which is possible at 800 by 800 pixels. And there's a couple of other exciting work in this area that is orthogonal to what we have been doing here. And it can also speed up rendering. So it seems like these representations become now also quite interesting for computer graphics applications. Now, in the final part of this presentation, I want to talk about generative models, in particular generative models of radiance fields. So what we want to do is we want to take this NeRF model that I've just shown you and build a generative model, a generative adversarial network that is able to sample novel shapes from a latent code, right? So the NeRF model that I've shown you before has been fit to a single scene. But what we're doing here is we're trying to learn a model that learns the entire distribution over shape and appearances. And then after training, we can take or sample a novel latent code and generate a novel object with a novel geometry and a novel appearance from this model. This is, of course, much harder than fitting a model to a single scene. And so we need to apply some tricks here to make this work, and also to overcome the problems with rendering speed. So the goal is to build a generative model for radiance fields. And what this allows us then is to train from unstructured and unposed 2D image collections. The NeRF model that I've shown you required still the camera poses. So you need to first run a structure for motion, a different structure for motion algorithm like CallMap in order to get the camera poses. Here, for each object, we have just one image, and we don't know the camera pose of this image, and we still want to make use of this model and make use of this information and train the model with this information. And the challenges include that we can't directly discriminate in 3D space. That's infeasible, and also the volumetric rendering is slow, such that even applying a discriminator in 2D space is hard. So what do we do? This is an overview of the model. In this case here, we have not a radiance field, but what we call a conditional radiance field, because we condition both on a shape descriptor that comes from a latent distribution PS and an appearance code that comes from a latent distribution PA. So it's a radiance field here that maps the view direction and the 3D point to the color and the density, but additionally conditions on the shape and appearance descriptors. Because rendering is so slow, we can't render the entire image here. So what we do instead is we sample rays only so that we only render a particular patch. We sample first the camera intrinsics and also the camera extrinsics, and then we sample a 2D grid with a certain location in the image and a striding and a padding, such that in this case it's a 5 by 5 pixel image emerges. In practice what we use is I think 32 by 32 pixel images that we render. You can see the predicted 5 by 5 pixel patch here on the right. So we only render those rays here. And then we can do the same thing for the image. It's like a patch gun. We do the same thing for the image, where we take from the image using the same distributions for the pixel sampling. We render a similar patch here and then compare these two, like in a gun, using a standard discriminator. And this is now very easy because we just have these two patches of size 32 by 32 pixels. So we can just use a standard and very small convolutional neural network to implement this discriminator and backpropagate gradients. Yes, and this works actually quite well. So here's an example of this model. On the top you can see the appearance that is generated and the geometry, and on the bottom you can see the 2.5D depth maps that are generated, and they are generated without inputting them to the model. This is emerging automatically from the model. The model has only seen RGB images at training time. Yet at inference time, we can also get the geometry. The geometry is needed, of course, if the model wants to do reasonable like appearance predictions. So it must implicitly come up with reasonable geometry. So we can do this for the cars here on Kala, but also for cats and birds and faces. And this leads me to GIRAFFE, which is an extension of this GRAF model, and which is this paper that we've presented at CVPR this year called Compositional Generative Neural Feature Fields. And the idea here is that, well, in real world scenes, we typically don't observe only a single object that's well separated from the background. So can we just, again, with 2D images as input, disentangle the scene into its individual components without any supervision, just through the inductive biases of this 3D bottleneck that we're imposing? And it turns out, to some degree, we can do this, yes. So what you can see here is we have a shape and appearance descriptor, now not for the entire scene, but per individual object. And we also sampled the pose of each of these individual objects and also of the background. And then we can composite them because they are all radiance field representations. It's very easy to composite them. And one trick that we're doing here is we're not directly rendering the radiance, but we're rendering features. And the advantage of rendering features is that when we render them to feature image, and we have displayed here a real image just for clarity, but what we have here as a representation is really a feature field. The advantage is that we can render this to smaller images, say 16 by 16 or 32 by 32. And because these features comprise more information, we can have a decoder that then decodes into 256 by 256 images. And this is really key to making this work, because otherwise it would be too slow to render images at high resolution. So we're using these feature fields in order to feed the decoder, the 2D decoder, to allow the 2D decoder to go to higher resolution. Okay, so here are some examples. This is an example of a 2D gun trained on the Clever dataset. And what you can see here is that it's very difficult to manipulate the objects because everything becomes entangled. But if we use our model that has this implicit or this inductive bias of the scene being 3D, we can afterwards manipulate each object individually. We can translate objects, but we can also rotate objects, some level of control that's impossible when training 2D guns. We can also change the background. And we can add more objects at test time than have been present during training time. Here are some examples on real data. This is for cars. Now we can rotate the cars. We can translate the cars. And we can change the distance to the cars or the size of the cars. We can move the background, in this case for the churches dataset, which is quite challenging. We can also change the background appearance. And we can even generalize to out of distribution situations. For example, we can translate the car further than it has ever been observed in the training set. We can also scale it further. And all of this we can do at inference time, while at training time, we have just used a collection of images without any annotations, right? Okay, that brings me to the end of my talk. I've demonstrated how neural networks can be used as continuous shape representations. And we've seen occupancy networks, but there's also other works such as deep SDF that predict sign distance fields, or scene representation networks, or NeRF. So I hope I could convince you that these coordinate-based networks are effective output representations for shape, appearance, material, and motion, as they don't require any discretization, and they can model arbitrary topology. And they can be learned from images via differentiable rendering, which we had a deeper look into. There's many applications: reconstruction, motion estimation, view synthesis, also robotics. Actually, the first result, the neat model that I showed you in Kala on the first slide, was also an implicit model that was using the same ideas. However, there's still quite some challenges involved that have to be overcome. First of all, we need to extract the geometry in a post-processing step, which takes some time. And extension to higher dimension, as we've seen, is not straightforward. Also, the fully connected architecture and the global conditioning lead to very smooth results, but there's some promising directions here. For example, we've seen conditioning on local features, such as in conv-onet, or also using better input encodings, as is done using Fourier features, for example, in NeRF. So thank you very much for listening to my talk. If you're interested in our work, I can also recommend to you our blog, which is linked here. And I'm very happy to, I'm looking forward to the discussion now and to your questions. Thanks.
Okay, thank you for the great talk. Let me stop the recording here. Yes, I think it was really nice introduction to 3D vision from the very kind of the fundamental idea about like the neural, the implicit, the representation to the very advanced ideas in the very recent papers. So it was really great talk. For the audience, if you have any questions, feel free to turn on your mic and ask the questions, or if you just leave the questions in the Zoom chat, and I will just read these questions. And while the audience think about some questions, maybe I can start first. So actually, I was just curious, like, so you have shown many nice works about like learning some input representations, not only for the geometry, but also for the color and the motion and the materials. But I also, this is like kind of the quick question, but you also show the like one example of like learning some like some material, the properties, not just the colors, but basically how the color should be changed based on some lighting condition, right? And so for that, is it just the case of like having some one more the variable for the lighting diffraction, or would there be some kind of the better way of like learning some sort of the implicit representations for the materials? Basically, you know, like if we think about like some BRDF kind of some representations for the materials, would it be possible to learn this type of the things with the implicit function as well?
Yes. So let me move back quickly to this one here. So this is, of course, just a surface light field, right? A surface light field means we can, well, in this case, what we did is we actually trained It's a little bit more than that. So what we trained with a point light source, because we trained entirely in simulation, and then we can then of course render the scene with a environment map, but we can't change the material, right? Still, so it would be very interesting, I think, and some people are going in that direction. For example, there is work from Saibi and Manmohan Chandrika from San Diego that look into how we can use this to model also BRDF. Light transport in general is of course very complicated, and if you include, we have also done some steps in that direction, but one difficulty of course is that the ambiguities that arise are just getting very large, right? So there's a lot of ambiguities when you model both the light and the geometry and the materials, and either you need a lot of observations, much more than we would need here for surface light fields, or you would need additional prior knowledge, which some people, for example, render synthetic scenes of artificial objects and use this as a source of prior knowledge, which I think is working quite well actually, and it could be valuable to resolve this here. And also one thing that, of course, many of the approaches struggle with is if you have even more complex light interaction. For example, if you have multipath, if you want to model multipath effects and shadows and so on, right? So this is, I mean, in theory, it's all possible, but the problem is first of all, is heavily under constraint, and then also at some point it becomes very slow because you have to render all these light paths. But there is, I think there's some exciting work in this direction, and I hope that we can see more of this in the future.
Yeah, for the answer. Yeah, the reason that I was asking about the material is that I was just thinking that maybe we can think of using some very strong, some prior knowledge as kind of the supervision, because I guess there will be some very specific patterns for the materials. Like we typically see like the plastics and the metals and I don't know, like some wood, like these might have some very specific patterns in terms of like having some specific specularity or some diffusions in the kind of some some material properties. So which means that instead of like learning like all possible sort of the input and the output the functions, like for all the incoming, the outgoing, the rays, we can think of like having some very specific, like sort of some list of some materials, basically learning some sort of the dictionary of like very specific materials, and just applying these, some learned very small set of the materials to some of the shapes. Yeah.
Yeah. So this is, I mean, this is definitely something, this is what I meant a little bit with like generating synthetic scenes and learning a representation for those, or you can use material databases, which are for not that large yet. I think we should have better material databases probably.
Yeah.
And then of course you can constrain the problem, and I think that's the way to go. Another property of this implicit representation is also something you can use. For example, texture has typically higher frequencies, and like also the view dependency doesn't influence the geometry, but only the color. And this is something that's already utilized in these models. Otherwise, they wouldn't work. It's kind of a hidden, a little bit a hidden secret. For example, in NeRF, that this architecture is designed in a very special way to make it work. Otherwise, it wouldn't work well. And the key is here where the conditioning information is injected and how the capacity of the neural network is adjusted to allow for certain things and disallow for others. And so the architecture plays a crucial role here as well. But it's of course a very coarse prior only on that you apply. But it's also still an important one.
Yeah. Okay, thank you for the answer.
Yeah, thanks for the question.
There's like one question in the chat. So we typically assume that the positional space is Euclidean, so that we can easily use the sinusoidal positional embeddings. On the other hand, what would be the appropriate positional embeddings for the INR if the target positional space is non-Euclidean? This could be useful if we deal with some fields of the smooth surfaces.
What is INR?
I guess that's the recent work about learning some implicit function like this.
Oh, now it went away.
Wait, maybe I'm not.
I'm not exactly sure what INR is.
Yeah.
Okay. I see.
Okay.
Good.
Just switching the two words in neural and the implicit.
Okay. Yes. Oh, wait. Now there's a new one. That's a good question. If it's a manifold, defining these. So I've seen people applying, for example, in the case of human, I think there's not that much work on this, honestly, but I've seen people applying these implicit models on human bodies, where you also have a non-Euclidean manifold, right? And you can define distances with respect to the human body. My guess would be that I guess also for these, depending on how you represent the input, these positional embeddings would still be useful, right? Because what they do effectively is probably, yeah, maybe you need to change them. Honestly, I can't really answer that, but what they really do is they solve a problem with coordinate-based neural networks. The problem with coordinate-based neural networks is that if you have a low input dimensionality, then the output is smooth, right? And you can show this. And so no matter what your manifold looks like, you need to somehow lift your input into a higher dimensionality, right? And so using random Fourier bases, I believe, no matter what exactly the manifold will be, will help you. But maybe there's representations that are better suited than others, and that depends on your manifold. Yeah, but it's a difficult question. So I can't. Yeah. Maybe one recommendation is also, I know that Yaron Lipman from Israel is working a little bit in this direction. So if you check out recent publications from his group, you might find something that's relevant to your application.
Yeah, thank you for the great answer. I also remember there was like where you work about like doing some like the convolution in the spectral space of these surfaces or some 3D. Basically in any manifolds, but I'm not quite sure how much this kind of idea is really kind of the practical to be used in these real applications. But yeah, these are also kind of interesting questions.
It's definitely interesting, yeah.
Yeah.
I have the chat now open, so I can also.
Yeah. I guess it might be better for you to just read the question because it's quite long.
Probably a bit easier, but the question is quite long. Okay, I think there is. The multiple questions? Okay. So the question is, I have a simple question related to implicit neural rendering. May I ask your thoughts on how to make efficient sampling compared to random sampling on implicit neural rendering? Oh, how to make efficient sampling compared to random sampling on implicit neural rendering. And do you think reducing sampling time is a current important problem on implicit neural rendering? Sampling points on array is easy for voxel-based methods as there is a finite set of voxels along with it due to the discrete nature of the 3D grid. For neural implicit representations, there is an infinite set of points along the array and the sampling process becomes challenging. Two of the most common ways to address this issue are sampling random points or regular points with random perturbations. For an example of voxel-based rendering, DVR minimizes the occupancy of an intersection point when encountering, okay, it's a long question. The projection to the silhouette is a false positive and maximize the occupancy of a random point along array when the projection is a false negative. Yes, so so the question is how to make the sampling efficient. So NeRF does it, of course, in this two, like NeRF has a hierarchical procedure where first like random points are sampled along array using regular distances plus noise jittering. And then once the surface is roughly determined, you can narrow down and sample more points there, right? This is for volumetric rendering. But similarly for DVR, we have also the problem, of course, that if we, so for example here, we have also this problem that if we would sample too quickly, then the start and the end point becomes too far away such that the second method would work. So Running the second method, which is a gradient-free method for finding the surface intersection, is very fast because it just needs 2 or 3 or 5 iterations. But first of all, you need to find roughly the interval where the surface lies, right? And if you have no idea where the surface is, then you have to really go along the ray. There's really not much to do to avoid this. However, if you have already a rough idea, you can make use of this. And maybe one work that I didn't have time to talk about today, but I can still show you, is UniSurf, that is kind of trying to build a hybrid between, this is ICCV also, is trying to build a hybrid between NeRF volumetric representations and surface representations like DVR. And the idea here is that, well, first, if you want to do 3D reconstruction, in the beginning you don't know anything about the surface geometry, right? So you have to really sample uniformly. But as you know more and more about your geometry, you can narrow the interval. And that's what's happening here. So there's basically, so it makes a connection between surface rendering and volume rendering, and it for volume rendering, it samples the interval successively smaller, such that at the end both are equivalent, right? And you can do this if you do it slow enough. You can do this because you get more and more certain about what the geometry of your object looks like, right? And then, of course, if you are very close to the surface, you can also get away with less points. So this is one way you can do it, but really, yeah, at training time, if you don't know anything about the geometry, it's very hard. You need a course to find strategy, I believe. Something either along the ray or in any other way, you need to go course to find. At inference time, it's easier, of course. So for example, in KiloNeRF, we use empty ray, early ray termination and empty space skipping, because if you know already the geometry, then you can build an indicator field, a rough indicator field, a hash table, and you can skip all the samples. You don't need to evaluate the network. You can skip all the samples where you're sure they are in free space, right? But this is only possible at test time or when you have a rough idea of the geometry. Does this answer the question?
Yeah, I think it's really good, great answer for the sampling question.
Okay.
Yeah, I guess we can move on because we are slightly running out of time. So the next question is actually about the paper that even you didn't introduce in your talk. So for your ICCV publication NEAT, it seems so the question is about like whether this approach can be generalizable to the other action-based videos such as discourse assembling or even surgery. Is there any kind of expected challenges in this extension? This is the question for the paper, the NEAT that you want to present at CCP this year.
Well, I mean, the approach that we have is kind of specialized for self-driving, I would say. But I think the underlying ideas are kind of general. So what we do in, I can show you here. Basically, the idea at a very high level, I hope you can see this. So the idea at a very high level is, the problem is with sensory motor control applications that typically the sensor information is very high dimensional and the action space is very low dimensional. And this mapping from high dimensional to low dimensional is difficult. And you need something that very quickly narrows down on the input information. And so what we are doing here is we have an attention mechanism that basically, using this implicit model, iteratively attends to certain input, to certain areas in the input. And I think that's a very generic concept to use for other applications as well. But then some things are, of course, very specific here. So what we predict here is waypoints. And if you would do surgery, you would maybe not predict waypoints of the tool. I don't know. So we predict waypoint fields here. And also we predict semantics as an auxiliary task, which is giving us like a multitask objective and improves performance and robustness. So I think you can do this for other robotics applications as well, but probably the exact output representations that you want to predict look a little bit different depending on your exact task.
yeah, I think that would be good answer for the question. And the next one is about the NeRF. So basically, the question is about like what are the some specific use cases of the NeRF in terms of the applications, like whether the NeRF can be used for some robotics task or some autonomous driving or some other robot intelligence.
Oh yeah. So one problem that we are currently trying to bridge is so we want to basically, so what I believe these representations are useful. So these implicit representations in general are much more useful for robotics than you might think, because the advantage of them is that you can query very selectively, right? So for example, for rendering an image, it takes a lot of time. It takes a few seconds, depending on which approach you're using. But in robotics, that's often not necessary, because you need to query only a few locations if you do it selectively, right? And then the query of one location is just microseconds, right? So that's, or like at maximum milliseconds. So that's basically something that I think is very useful for robotics, because if your robot, wants to query just in this direction, is there an obstacle or not, then this is much faster than potentially other approaches. So this is, I think, one use case of these applications, and that's something we use in NEAT. One thing that doesn't work yet, and I think we should work towards, is building these photorealistic simulators that don't just are not just able to optimize for a single scene, but also build compositional models of larger spaces. Because what this would allow us then is to build simulators automatically. For example, in the autonomous driving work that I've shown you, we are working with the KALA simulator. And the KALA simulator is built by a team of more than 30 people. Half of them are designers and artists that create the assets, make sure everything looks right. And even then you have this uncanny valley that the renderings don't look like real photos, right? So you're still far from the real images that you would record with a real self-driving car. Of course, you can try to overcome this with domain adaptation techniques, but what I think would be very interesting is if we could, using these techniques of novel view synthesis and building generative models, which together don't work super well yet, as you've seen, like the NeRF produces very high fidelity results, but the results with GRAF, with this generative model, are still kind of not at the level of quality as we like to have them. But if you could do this, then you could go around with a car, let's say, or with an indoor robot, and build photorealistic simulators where you can manipulate objects. And then you can, if this is fast enough for rendering, at rendering time, like in KiloNeRF, for example, then you can deploy your robots first in a real world replica. And I think that's very valuable, because there you can do much more testing and evaluation, and you can't kill anyone, for example, and you can test and validate your systems. It's also important, if it's about safety systems, it's important that you validate your systems properly, and you can't really validate safety critical systems in the real world. So I think it has applications there.
Oh, yeah. Thank you for the answer. The next question is also about the NeRF and also about the light transport. Due to the appearance of the NeRF, the volumetric rendering seems to be a hot framework in the 3D vision for the high quality rendering. How can the topics be integrate and aid the light transport frameworks like the ray tracing? And also, which one do you think is the promising when constructing the end-to-end trainable rendering framework, either the volumetric rendering or the light transport?
Well, I don't see such a big discrepancy here. I mean, when we are rendering, no matter if we're rendering surface representations or volume representations, we are rendering by marching rays, right? And of course, we can model BRDF functions at the surfaces, or even scattering functions, which are not at surfaces, and collect information from multiple rays. I think the main challenge here is as also is a challenge actually for bidirectional path tracing, let's say, is the runtime, right? So if you have time and you want to render a movie, and it doesn't matter if you render like 1 hour per frame, I think then it's feasible. But if you want to go to real time, it's actually quite challenging. So yeah, but in general, I don't see a big I mean, I don't see a big difference here. It's easy to and there are works that are going in this direction. It's easy to send rays either from the camera or from the light sources and move through that volume and then create an image from that using both surface and volumetric rendering techniques. It's more a matter of time budget and also the rendering quality that we want to achieve. And if you choose a surface rendering or a volumetric representation, purely, I think, depends on if you want your models, like if you know something about your scene, basically. If you know that your scene is composed of solid objects, then there's not really a need for going to volumetric representations, but you can go to surface representations like DVR. But if you want to represent transparent surfaces and things like fog and so on, then of course you have to have a representation like a radiance field. And maybe also these hybrid representations like Unisurf that I briefly showed in the end. And a couple of, there's Noise, and there's also a paper by Jaron Lippmann's group in this direction that combine volumetric and surface representations. I think could be a valuable direction to pursue in this area.
Yeah. Cool. Yeah, thank you for the answer. Since there is like the huge interest in NeRF, let me ask one quick question in high level the question, which might be a little overlap with some previous questions. So we are basically seeing like some very high quality the outputs from the NeRF, but we are also seeing some kind of the certain limitations of the NeRF in terms of that it's very hard to kind of edit the shape and also the colors, and yeah, the rendering time might kind of be solved by your paper and also the other papers, but also it's not easy to make some sort of the deformations. It's not also that easy to like encode some sort of the emotions, the animations. And also, as you also mentioned, like if we consider like some sort of the physical interactions, probably the NeRF may not be the best choice. So how you kind of sort of like see the future of the NeRF, like how can we kind of overcome this kind of the limitations in the future research, and how do you think that how this kind of the NeRF types of the representations will be kind of the advanced in the future research?
Mm-hmm. So I think one, like if you want to animate scenes, for example, so here, this is not NeRF, this is a surface representation, it's called SNAV, but it's going in the direction that you're asking, right? So animating is of course possible if, for example, if you have a skeleton and you can learn the blend skinning, then you can animate your objects, right? And you can animate both surface representations and also radiant fields representations, as we have done here, and even generalize to very to novel unseen poses. So I think that's one direction to pursue, and many people are interested in this at the moment. We have done this for humans, but of course it's also interesting to do this for other type of objects, rigid and non-rigid objects. If it's rigid objects only, it's easier, right? For rigid objects, you could basically just, like in the case of GIRAFFE that I've shown you, you could just build individual radiance field representations for individual objects and then manipulate them in terms of their pose. What's harder, I think, is to manipulate like the object appearance and maybe build a good shape representation. We haven't bridged the gap between generative models that work very well in the 2D domain, like StyleGun, and are controllable, and generative models in the 3D domain, like GRAF and GIRAFFE, and it's non-trivial, but I think that's also something that that will be one of the next steps to solve.
Yeah. Actually, following that, this is the last question, but in terms of like learning the generative models, for the 2D domain, like we have seen like great success with the StyleGAN, the StyleGAN, all these things, which are really creating, real like images. But I feel like for the 3D case, the GAN or some generative models is kind of some challenging problems in terms of like how we basically create some real like the shapes, not just making some. I mean, obviously, like you have some really some great results of like some gentle models, but some people might kind of see that like how can we achieve some results like this tile again or this tile again, which is really making some real like the photos for the 3D case as well. And obviously for the implicit representation, there is some sort of the limitations in terms of like that, as you also mentioned in the last slide, like getting some sort of like smoothing some sort of the outputs or some kind of the other limitation. So how do you also envision like some learning some data models in this 3D space, and what would be kind of some ideas or some directions that we can improve the quality of the generative models?
Yeah, that's a good question. If I would know that. So we're trying. So one thing that I think we should get rid of is like we have these two very different approaches of handling the problem. One is like fully supervised and the other one is fully unsupervised. And I think we need to find something in between, because like, for example, in GIRAFFE and in GRAF, assuming the fully unsupervised case where I just have a collection of images, this is kind of unrealistic. Also, humans don't learn like that. Like humans have a curriculum, they learn with easy objects first and they build up and they have some innate knowledge as well in their brains. I believe like it's actually impossible. Like you can go only so far with these unsupervised methods. And this is limiting us also in terms of fidelity at the moment. But there is some very simple sources of knowledge that we can use, right? And why shouldn't we use these sources of knowledge, right? There's pretty decent 3D reconstruction pipelines, and there's pretty decent, I don't know, even single image depth estimation. There's good CAD model collections, which we could connect to these implicit representations. There's some people trying to build implicit models based on the CAD models. We do have a very good instance segmentation these days, and we have pre-trained models for all of this, right? So it feels like a bit silly to not use this information. And I think it's kind of something, you need this knowledge in order to make progress. And then the other thing, which is not clear yet, I think is the architecture, right? So maybe it's the case that the NeRF architecture, or this MLP, in general, this MLP architecture, works well in fitting to a single object, but it's harder to actually build a latent space for it, right? That could also be. And maybe we need a completely different architecture here. And that's something that I think we don't know yet at the moment.
Yeah, thank you for the great answer. I guess these answers will really inspire many of the students here who are especially interested in this 3D vision. And thank you for the great talk. I think we are running out of time, so I think we need to stop here. Thank you for the great talk, and I hope that we can also invite you again sometime in the future, especially in the physical place after the pandemic. So thank you for the talk.
Super.
And also for the audience, basically you're gonna continue this colloquium talk not on the next Monday, but on the next Friday. Cool. So I guess we can stop here. Thank you.
Thanks.
Thank you again.
Thanks for having me. Have a good week. Bye-bye.
Bye. Thank you.